will not be same as the transmitted frequency is. So, this is called Doppler effect. So, continuous waves radar CW radar, they operate on this effect, and once we know that if there is a shift in frequency, that shift is called Doppler frequency shift, delta f we denote it with. So, if there is delta f, it means there is a relative velocity between the transmitter and receiver, or in other words we can say that either transmitter or receiver, they are moving. So, when we have delta f or when we have Doppler frequency shift, it means we have the velocity also. So, the proportionate velocity can be calculated if we have delta f. Next form is pulse radar. The radar which I explained with the help of duplexer is a form of pulse radar. What happens here? Here the transmitter transmits a train of narrow rectangular shaped pulses modulating a sine wave carrier. The range of the target is determined by measuring the time taken by the pulse to travel to the target and return to the radar station. We just have discussed the operation of pulse radar. There we had the transmitter, we had the receiver, we had the duplexer, and the time taken by the pulse to travel from target and return back to the radar station was calculated, and that time, as we know the velocity, we can calculate the distance or we can find out the range. Now, we will discuss a very important term, radar range equation. This is very important equation. Radar range equation relates the range of radar to the characteristics of transmitter, receiver, antenna, target and the environment, and it is used for radar system design. Any radar system, if it has to be designed, it will be designed on the basis of radar range equation. Here we have a radar. So, once the signal is transmitted, say this will be transmitted. Here I show the isotropic radiation pattern. Once the signal is transmitted, it will be transmitted in all the directions, and we assume that it is an isotropic antenna with which we are transmitting the signal for the derivation of radar range equation. So, it will be transmitted in all the directions, and we assume a particular at a particular distance r we have the object. So, what will be the intensity of signal which will be reaching at the at this location? It will be Pt, means transmitted power, divided by 4 pi r square, because 4 pi r square, this is the surface you all know 1 by 4 pi r square is the surface area of any sphere. So, if we assume that signal is transmitted in all the direction. So, the same signal is present here, same is here, same is here, and in all the direction if it is present, what is the strength of signal, what is the proportion of signal which is present at our target location is this fraction of the total power. Now, when we consider the another case. Now, signal comes back, directional pattern. Now, we have a directivity. We have an antenna which has got directivity. Now, when signal will be transmitted, it will be transmitted more in a particular direction as compared to other directions, and how, what is the extra dimension of that signal, what is the extra proportion of signal in that particular direction, it will depend upon the directivity or directional gain of the antenna, transmitting antenna. So, if G is the gain of the antenna, then this is the proportion of power which should be available at this distance r, but because of G it transmits more power in this direction. So, G is the gain. So, by this factor G, more power will be reaching at the object. So, now power reaching at the object with an antenna having a directional gain G is P T G over 4 pi r square. Now, the maximum range of radar is the distance beyond which the target cannot be detected, and this happens when PR is equal to S minimum. S minimum is the minimum detectable signal. So, maximum range means R maximum will be PT, this is directional gain of antenna, this is the area, effective area of the antenna, and this is the gain. Then we have 4 pi square S minimum. S minimum is minimum detectable signal. So, lesser the S minimum, more will be the range. Lesser the S minimum, more will be the range, means if the receiver is capable of detecting lesser signal, it means that radar system is capable of detecting more range. And very important thing which is to be noticed here is this is 1 by 4th power, it is all power 1 by 4th. So, whenever you get a question, you should keep this thing in mind that this is power 1 by 4. Factors affecting range of a radar. What are the factors which may affect the range of a radar? From the equation it is very clear. First, it is transmitted power, second it is the frequency at which you are operating, then radar cross section area of the target, from which area the radar the signal is being transmitted, minimum received signal or S minimum or minimum detectable signal. So, these are the factors on which the range of a radar depends upon. Then we discuss about the maximum unambiguous range. What the ambiguity is? Sometimes what happens, we transmit a signal, but we do not receive any reflection or we do not get any echo signal. Then second pulse is transmitted and you do not receive any signal, then third pulse is transmitted and you receive a signal. So, if such a situation arises, then the confusion is that the operator does not know that the received signal, echo signal is from pulse number 1 or pulse number 2 or pulse number 3. So, such a situation if arises, this gives rise to ambiguity in the range. So, the operator may not be knowing that what is the difference between the received signal and transmitted signal, whether it is to be calculated from pulse number 1 or 2 or 3. So, such a situation if arises, that is called ambiguity. So, how it can be avoided? Range unambiguity, maximum unambiguous range, how we can get the unambiguous range. So, very simple, this is the example. First pulse transmitted, no signal, second transmitted and we get the echo signal. Now, confusion is whether this echo signal is from T1 or it is from T2, it is not sure. So, this is such a situation if comes, this gives rise to ambiguity. So, this ambiguity can be overcome if we change the shapes of the adjacent pulses. Suppose the width of this pulse would have been more, then we would have been in a position to tell, because the width of echo signal would also have been different. So, we would have been in a position to tell that this echo signal is from target from pulse number 1 or pulse number 2. So, in this way we can overcome this ambiguity. Here is the block diagram of a pulse radar. Here are the various blocks which show the various components: trigger source, modulator, microwave oscillator, duplexer and antenna. It shares the antenna through duplexer. So, this is the transmitter section. Here is modulator, trigger source and microwave oscillator, microwave generated from here, fed to the duplexer and it is transmitted. Reference signal is given to indicator for the purpose of calculation of range. Here the received signal, it comes to the duplexer, comes to mixer. Here we have the local oscillator. So, the combination of these two generates IF. Now, angle is achieved from another feed we get from the antenna. IF signal is fed to the detector and it goes to the video amplifier. After video amplification, it is given to indicator. Now, indicator gets two inputs for range equation, means one is from the transmitter, other is from the receiver. By getting the difference of time between the transmitted and received pulse, the distance can be calculated. Angle is another factor which is calculated by getting another feed from the antenna. So, these are the various constituents: trigger source, pulse modulator, microwave oscillator, duplexer, low noise amplifier, mixer and local oscillator, IF amplifier, detector and video amplifier, indicator or display, direction indication from angle data as has been explained. Limitations of simple continuous wave radar. A continuous wave radar has got some limitations. One is lack of isolation between transmitter and receiver. Receiver may burn out, masking of wanted signals by transmitter noise, introduction of flicker noise due to homodyne, lack of meshed filter in the receiver, unable to identify whether the target is approaching or receding. It cannot tell whether the target is coming towards the radar or it is going away from the radar. Increased clutter, clutter means the noise compared to the pulse radar has got lesser noise as compared to CW. Measurement of range is not possible by CW because there is no pulse, there is no marking, the signal is transmitted continuously. So, it is for speed measurement only, the distance cannot be measured. MTI and pulse Doppler radar. So, to overcome this another radar MTI and pulse Doppler radar is used. It is MTI is moving target indicator radar which has got the properties of CW and pulse radar. Now, we will discuss the microwave devices and components. There are certain microwave devices and components. What these are? Active microwave devices, klystron, magnetron, travelling wave tube, backward wave oscillator, gun diode and impact diode. Microwaves has got special purpose devices which are used for microwave frequencies only. So, these are those devices: klystron, magnetron, travelling wave tube, backward wave oscillator, gun diode and impact diode. These are called active microwave devices. Passive microwave devices are directional coupler, junction tees, isolators, circulators, resonant cavities. They do not have their own signal, they do not have their gain as such, but they are the helping objects, helping devices which work with the active devices. And third is microwave measuring equipments. There are two broadly equipments which are used for measurement of microwaves. One is power measurement, power meter, and second is for measurement of frequency, which is called frequency meter. Displays, there are two types of displays. One is A scope. A scope is like this. It shows the range in a plane, means it has two components, horizontal and vertical components, and this is the target location. All this is clutter or noise. So, this is target. So, A scope is one type of display. Second type of display is plan position indicator. It shows the positioning of different objects around the radar antenna. So, this is called plan position indicator. In a plan, it shows where are the objects placed. It is a type of map. You can see this here. It moves like this, and wherever is the object, a point is placed there, and when we combine those objects, we see a structure like a map. So, this is plan position indicators, means here is the radar placed and where are the targets around this radar, it can be detected by PPI. So, with this we come to end of this chapter. Thank you very much.